Here we have a circus performer, and he's on a tightrope that's stretched out between two towers. He strikes one end of the rope and sends a wave along it toward the other tower. He notes that it takes the wave 0.8 of a second to reach the opposite tower 20 meters away. If a 1 meter length of rope has a mass of 0.35 kilograms, find the tension in the rope. So let's start with calculating the velocity of the wave. So the speed of the wave is, again, defined by distance over time. So the change in x over the change in the time interval, 20 meters divided by 0.8 of a second, gives us a velocity for the wave of 25 meters per second. So the mass per unit length of the rope then can be calculated as mu equal to the mass times the length. So we have a mass of 0.35 kilograms. We have a 1 meter length of rope. So the mass per unit length is 0.35 kilograms per meter. So by using the relationship then for velocity, using frequency and the square root of frequency and mu, we have the square root of F divided by mu, and we can obtain then the velocity squared is equal to F divided by U. So we end up, it's not the frequency, that's the force, the tension. Sorry about that. That's the tension. The velocity squared then is the force or the tension divided by mu, the mass per unit length. So we end up with the force equal then to the velocity squared times mu, 25 meters per second squared, 0.35 kilograms per meter, gives us a tension in the rope of 219 newtons. In this one, we have a 500-gram block that's released from rest and slides down a frictionless track that begins 2 meters above the horizontal. So you can see we're getting set up for a potential energy problem here. At the bottom of the track, where the surface is horizontal, the block strikes and sticks to a light spring with a spring tension or spring constant of 20 newtons per meter. So we can see that in the diagram here. Potential energy, we're going to have some kinetic energy, and we're going to have some energy due to the spring. Since the spring is considered light, we can neglect any small amount of energy lost in the collision with the spring and apply conservation of mechanical energy from where the block first starts until it comes to rest. So again, we rely on our conservation of mechanical energy relationship, kinetic energy, potential energy due to gravity, potential energy in the spring, initial, same thing, final. We expand all of those terms, again, like we've done before, 1/2 mv squared, mgh, 1/2 k x squared, and the same thing on the other side. So now, again, we look at determining which of these terms goes to zero because the object is at rest or there's no energy there. Well, to start with, the object's at rest, so that goes to zero. We have the potential energy, mgh, and we have the spring at rest, no compression, zero. On the other side, the final side of the equation, we have 1/2 mv squared, then where the object comes to rest, again, zero, 1/2, or the mass and the gravity and the height, the potential energy goes to zero, and we have all of the energy now in the spring. So now it comes down to the height of the box equals to the energy in the spring. So let's move things around so that we can determine that maximum distance the spring is compressed. We end up with x squared, maximum compression, 2 times mgh, the potential energy, divided by the spring constant. Square both sides, we end up with the square root of that value, which equals then 2 times 1/2 kilogram, 9.8 meters per second squared for the acceleration of gravity, 2 meters divided by 20 newtons per meter, the spring constant. And we get a compression in the spring that you can see over in the diagram. X max is equal to 0.9 or 9/10 of a meter.